and welcome to Machine Learning, Artificial Intelligence and Simulations with Unity.
Hi everyone, my name is Paris. I help run a studio in Tasmania, Australia called Secret Lab. And this is my wife, Mars, who is a computer science and machine learning researcher. We write books together and do all sorts of stuff. It's really fun.
So many things other than books. We do lots of things together. One of the things we do together is we like to find the overlap between our two different domains of game development, and I do lots of things with machine learning, but machine learning is the thing that underpins them, and the thing that you can do with those two things combined, by our powers combined, is make bots in Unity.
So we're talking specifically about combining Unity with the amazing machine learning community full of tools like PyTorch and TensorFlow and things like that. Unity has a machine learning toolkit, which we'll come to in a bit, which uses PyTorch. We're not going to teach you Python or PyTorch today, we're going to gloss over that bit, but we are going to be using it. So today's topic is the combination of Unity and machine learning tools. If you have any questions as we go, feel free to tweet at us.
So today we're going to do a brief intro of where the type of machine learning that UnityML Agents uses fits into the broader domain of machine learning. Then we're going to gloss over the main beats of the UnityML Agents framework and the kind of concepts it introduces to Unity. I'm going to make a minimal bot very quickly live. And then we're going to talk at the end about how you could extend those concepts and add in other modules to make it more powerful, or have bots that then could be applied to real-world robots, cars, or anything you can imagine.
So let's start with a brief intro to machine learning for someone who has maybe heard of it but not done any.
So, the kind of machine learning you might think of is usually going to be some sort of image classification or object detection, or it might even be something like fraud detection, anomalous behavior detection. And that all falls under an umbrella called classification tasks, where you have some model that observes a bunch of input data, where you have some input data points and some label that it represents, and then you want it to learn, okay, well, if that's however many examples of that label, anything else I see that's similar to those, that must be this label. So a classic example is is this a cat or a dog photo? And if you had to write a rule-based system for that, that would say, okay, well, if it's got pointy ears, it's a cat, but I guess not if it's a chihuahua, and if it's small, but then it could be something big like Kelpie that has pointy ears, it's gonna get really complicated. But if instead you give it 1 million photos of cats and 1 million photos of dogs, it can go through and it can find its own internal representation of what's consistent within that group, but not between them. Then you can give it a new photo, and it's going to go, what's it more similar to out of these different labels that I have? And that applies to anything where it's like, this was fraudulent behavior, this was legit user behavior, this was pedestrians walking in front of a car, this was not a pedestrian, it was just a wiggly man. Anything that you can put labels on, you can teach it to find what's different between those different labels. But UnityML Agents is a different type of machine learning that I would say is kind of, when you get really down to it, a subgroup called reinforcement learning, where instead the thing it's trying to map between is what input it gets, what observation it has of the world, and what actions that it should do in response. So this type of machine learning is when you want to train something to have complex behaviors, not just recognition. It's going to be in some situation where it needs to do something, and it needs to learn for each situation what the right thing to do is. So the gist of reinforcement learning is that if you had some scenario where describing the complete list, exhaustive rules of all of the situations it could be in, and then how it should respond is too complicated, what you can instead do, because we have computers and they're really fast,
super fast,
is you just let it do random behaviors and then reward it every time it does the right thing, and it's going to go, oh yes, that was right, and eventually it's going to map a pattern of what was consistent about the things it did when it got some reward versus when it didn't get a reward or it got a negative reward.
Isn't that just trial and error?
Well, yes, very clever, but really fast.
Okay.
So here's an example. In this example, we're going to get our colleague, Dr. John Manning, to be a bot. And we want to teach him to always walk towards our other colleague, Dr. Tim Nugent, wherever he is. And instead of having a bunch of rules of wherever Tim is in the world, find him, John, and then seek him, we're just going to give him no information and we're going to reward him.
Might walk forward. Have a minty. Thank you. Ah, brilliant. Oh, I might take a step backwards. Give me that minty back. Guess I'm walking forward. Have a minty. Yay!
Okay, so that example, we can see that John had no information to begin with, and when he walked towards Tim, he got a minty, and when he walked away, he had it taken off him. You can infer that he did the right thing in that case, but if Tim moved next time, he might not know. He might think he still has to walk in that direction. Maybe he didn't figure out that he had to walk to Tim. So he'd have to have a lot more attempts. And eventually what he would do is he would build up a policy. A policy here is a mapping between the inputs that you got and the rewards that it got at the end. So if it got a reward, it goes, oh yes, the thing that I just did and the observations I have now, those are correct because I got a reward. So here, the inputs are some observation of the state of the world, representing whatever diverse scenarios you have, and the responses are just the actions that will result in the most reward of the things that you've tried. So when Tim is in front of me, step forward. When Tim is in a different direction, turn to face him, then apply rule 1 again. So here, this policy is learned during that training phase. So from that first example where John starts, he has no information until he stepped forward the first time. He's never received a Minty. He has no idea. So the first thing that happens is an observation. The agent observes something about the world around them. Then they take an action, and then they will receive a reward. Then once they've got that one reward, they're like, okay, well, I know that that was good. Now let's take a different action and see if that gets a reward or not. So now let's talk about how this works in specifically ML agents for reinforcement learning.
So ML Agents is an open source project that Unity ships that allows you to do ML reinforcement learning with Unity. It breaks things down into 5 conceptual points. There is an agent, a thing that does something. That agent lives in an environment, the place it works, it lives, it does its thing. The agent has certain actions it can do to affect that environment or the things in that environment. The agent collects observations about that environment. It knows things about the environment and the things in the environment. And it receives rewards, which can be negative, when certain things happen in that environment or when certain objectives are achieved in that environment. So let's have a look at that in the context of the Dr. John robot we just looked at. Here is our John robot. The agent is Dr. John Manning. The environment is the local park in Hobart, a lot like Wellington. The actions are step forward, step backwards, and turn. He can see Tim's position, and he knows his own position. And he gets a reward when he moves towards Tim, and he loses a reward when he moves away from Tim. Pretty straightforward. Here's some examples in the actual Unity space. Here's a cute little cube that can rotate on different axes, back and forth, side by side. It has a ball on its head. It exists in a formless void. It knows its own rotation, and it knows the position and the velocity of the ball that's sitting on its head. It gets a very small reward every step of the simulation, every tick, that the ball is still on its head, and it gets a very large reward if the ball falls off its head. Terrible.
Negative reward.
Very negative, large negative reward if the ball falls off its head. Terrible, terrible, terrible day. Now here's another one. Here's a cute cube that is designed to push another cube into a target. Basically, it has a whole bunch of raycasts, so it knows its environment, and it gets a very small existential penalty, a negative reward, every step of the environment. So it's penalized for existing. So it's trying to push its block into the target as quickly as possible while minimizing that existential reward. It's a very tragic existence.
So it means not only do the right thing, but do the right thing and don't dawdle.
Exactly.
Faster is better.
Here's another one. This is a cute cube that needs to touch the various blocks around the circular edge of the environment in the correct order. 1 to 20 exists, but not necessarily always there. So it needs to touch the correct places in the world in the correct order. So it needs to touch 2, then 4, for example, then 5 if 3 didn't exist, and so on and so on. It gets a very small existential penalty each step as well, and a very large reward for touching a cube in the correct order, and a very large negative reward for touching a cube in the wrong order. It eventually learns to touch the cube in the correct order, thus lighting them up green. Here's a walking spider that learns how to walk by moving its legs, which are the actions it has. So it has the ability to move and rotate each of the joints in its legs. It is not animated to walk, it learns to walk. And it knows the rotations and angular velocity and positions of each of its joints, and it knows the position of the cube it's seeking. And eventually it learns to walk and seek that cube. Pretty
Which is
cool.
quite interesting, because it might not learn the way that a quadruped would normally walk with that kind of arms. It's going to learn whatever gets it there the fastest, because that gives it the best reward.
It skitters along.
So if we then have a look at that in Unity, the agent is just a game object that you give a script that is a subclass of agent on it. All of a sudden, that game object is an agent. Its environment is whatever Unity scene you put that agent in. Its actions are whatever functions you give that agent script that will change something about the agent. The observations are any inputs that you give to the agent script. And the rewards are wherever you call a set reward give reward function to. So it's highly modular, hugely flexible, only bounded by what you can do with a single game object in Unity.
So let's do a bit of a live demo. We're going to put Mars on the spot here, who's going to do this on her computer. We'll build a little agent in front of you and show you how it works.
So here we are in Unity, and we have a brand new empty sample scene. First thing we're going to do is we're going to install Unity ML agents. So here in the package manager under Unity registry, we have ML agents, and we're going to install this one. I'll have that one, please.
If anyone hasn't used Unity Package Manager before, this is Unity Package Manager. For those of you who have, this is Unity Package Manager.
So I'm going to make a little sphere that learns to seek a target. So in this scenario, the sphere is the John bot and the cube is the Tim. So first thing we need a floor so they don't just fall off into the void.
I love falling off into the void.
No, you love not falling off.
I love not falling off into the void.
Exactly. We're going to make a sphere. It's going to be called agent. It's the agent. We're going to put it on the floor. Then we're going to add a cube. It's going to be called target. We're going to put it not inside the agent. So we've got our little scene. We've got our agent, we've got a target, and they're on a floor that they can't fall through if we give the agent a rigid body and move around.
We're also going to tag the target with target.
Yes, we will do that. Target.
We're using Unity's tag system to add the tag target to the target because we'll use that to make sure that the agent knows where the target is.
Just slightly easier than finding game objects by name. We can find game objects by target. It's the only thing called target. It also means that it extends to if you have multiple targets, it would find one of them at random. However, designing it this way also means that if we get to the end and we have an agent and it's learned how to seek the cube, you can duplicate the game object of the agent and put 1,000,000 of them and they'll all work in sync to seek the cube. And we tried this the other day and they act like a flock of birds. It's very interesting. They're all trying their hardest. All right, so we've got our agent. They're all in the right spot, but we need to make our agent actually an agent. So here we're going to make a script. We're going to call it a ball agent. And we're going to put that on our agent. Ball agent. All right. Now, if we open ball agent, what we want is we don't want to inherit from mono behavior. Instead, we want to inherit from the superclass agent that comes with ML agents, which means that this is going to have the ability to be requested actions and be given rewards and receive observations. And when we just get all that behavior for free, we don't have to implement it ourselves.
This is what we imported when we used the package manager.
Yes. So now we're going to give it some information. We're going to give it a field that we can toggle from in Unity to change the amount of reward that it gets for touching the target. If we wanted to get a big reward or a small reward, it's going to have its rigid body so that it can be able to move, and it has a stored transform for the target. So it can be given observations of where the target is, so that if it knows where it is, knows where the target is, then it can figure out how close they are. All right, so we're going to give it a start method. When we first start, we want to find the thing in the scene that has the tag target, because we just gave our target the tag target, and then we're going to store its transform so we have a handle to it at all times. And we're also going to get our own rigid body so that we're able to move. And then we need to override a function that comes with agent called onEpisodeBegin, which means while we're doing this training cycle, everything happens in episodes where you have a certain amount of time where the agent gets either a certain amount of steps to perform actions and it gets to attempt stuff. As we said, it's going to act randomly. So usually the reason why you have this episode is that if you just had it all be one episode, it could get into an unrecoverable position, or it might just have an exploding number of observations that it would have to make about all the different states that the world could be in. In this case, we're going to make it that it's going to start with the sphere in the middle of the plane, and if it touches the target moves. If it falls off the side, it ends the episode. So then it gets reset back up the top, and it's like it gets its memory wiped, and it only learns only the good outcomes from the last thing. It remembers where its rewards were. And what we've said here is if its Y position of the agent is less than 0, that means it's fallen off the side. We're going to reset its position, and then whether it's fallen off the side or not, if it's achieved the objective or fallen off the side, we're going to move the target to a new random position. So now we can make these functions, just gets the rigid body that the sphere has and tells it that your angular velocity and your velocity is 0. So if you've just been pulled out from the void, put back up the thing, you don't want to still be moving downwards like you were, otherwise it's going to like mush into the plane and might cause some physics confusion. And then we're going to move target to new random position, which just gets a random point on that plane floor. So now we need to give it some actions. We need to make it able to move. So we get this function called onActionReceived, which means when it's training and when the model is trained, the agent has this thing called a brain. We're going to conceptually call it a brain, where that is the thing that's observing the training steps. So I see that when you touch this target, or when the distance between you and this target becomes 0, you get a reward. Ah yes, I see. That must mean touching the target is the objective. So then it's the thing that then passes out actions when you set the next challenge, you reset, and now the target is in a different position. The brain is the thing that goes, okay, move in this direction. And the way that it hands that down is through action buffers. You pick the structure of your action buffers. Usually it's going to be a vector of a certain size, and in this case we're just going to be a vector of size 2, where it's going to pass down an amount to roll on the x-axis and an amount to roll on the z-axis. And those things combined means that it can move. That is all you need to roll a ball in all the directions, is just these two numbers. And we've just multiplied it a bit so that it can use a nice value range. However, that's when the brain is controlling it. So that's the thing that's going to learn when it's making a neural net and it's observing the training. But we also want to check that they're hooked up correctly. So usually what we do is we do this thing called heuristic, which lets you control it. And we're going to do the same thing where it can also take key inputs.
Unity will compile, because that's what Unity does best.
Is it what Unity does best? Of all the things that Unity does, that's the thing it does best?
Certainly does it a lot.
All right, back in Unity, we need to give our agent 2 more things so that it's able to receive input and also to be the thing that passes actions. So the 2 things that we need, both from the ML agents, is a behavior parameters here, which you give it how many observations it's going to have, and we are going to give it, and it's going to have just 2 actions, which, like we said, it moves on those 2 axes. And we can call it ball agent behavior. Awesome.
Also, decision requester, which is another script from ML Agents Toolkit. Basically tells it how often to ask for a decision.
Yes. So in most cases, your simulation is going to be step-based. Like the agent will do something and it will have some outcome, and then the agent will need to go, okay, what am I doing next? And then the training brain or the complete model, if you've finished training, will go, this is what your next action is. But because it's a ball and it might already have applied some velocity and be moving towards something, it doesn't always need an updated action because it might still be waiting for its previous action to have the intended effect. So if it's just going to push in that direction, it kind of needs to skip a few steps until it wants to change direction. So this is just allowing it to have ongoing effects from its actions.
If you're using this for a video game AI, you could also use this to occasionally request a decision from the machine learning system to make your otherwise conventional game AI appear really smart every so often.
All right, let's see if it can be controlled. Yes. Ah! So that's how we know good for machine learning to do, because it's quite hard for a human to do. Okay, so the next thing we need to give it some observations. Since we've told it it's going to have 8 observations, we need to give it 8 observations. And what we're going to do is we're going to get the agent's own position, and then for its movement in either direction, it needs to know how much it's moving this way and how much it's moving that way, which is based on its recent actions, how much it's been pushed. And then you also get the transform for the target. So it knows where it is, it knows where the target is, it knows how fast it's moving on 2 different axes, which is, because the transform is at XYZ, it's a vector 3, so the agent's position is 3 numbers, and the target's position is 3 numbers, and then it's the agent's current movement along each axis. Another 2 numbers. 2 fingers, dear. 8 numbers.
Game development things.
The last thing we need is the important part. We need to give it rewards so that it can infer what its objectives are. In this case, we want it to be able to touch the cube and get a reward so that it knows, oh yes, I should touch the cube.
Cube good.
And it should also know if it falls off the side. So the first thing we're going to do is we have a fixed update. So if it's fallen off the side, we end the current episode. We want to reset this poor thing so it doesn't spend the rest of its existence falling endlessly into a void. And the other thing is if we have collided, which we do by implementing the on-collision enter because the sphere has a collider and the cube has a collider, we're saying if the thing that we have collided with is the target, set a reward to reward, which is that field we had back up the top of the thing that we've set to 1 in the editor, which is how much reward it gets for touching the target. And then we also want to end episode, which will not reset the agent's position, but it will re-shuffle, re-roll the target's position.
Yep.
So you won't visibly see the episode end in this case, unless you did like a debug log, but it's just getting a checkpoint that says you did good in this episode versus if it fell off the side, you did bad in this episode. Because it doesn't reset back to the middle, it might have gotten the last target but invested too hard and is now going to go off the side, whereas this means not only does it have to seek the target, but it also has to make sure that its movement is recoverable.
Right.
So back in here, now we're going to call ML agents -learn with our ball agent.
So ML agents learn is a part that comes with the Python installation of ML agents from Unity.
Okay, so now the way that Unity and Python are going to talk to each other is they're listening on a port. And we need to go back into Unity and we need to press play. And then it started its random actions. Oh look, it's already succeeded a few times. That's so fast. All right, so we're done. And it's output a .onnx, which is a neural net file, into our results folder. So if we go back up here and we go into results, first run ID, which is the run ID that we gave it, we have a .onnx file with the behavior name we gave it. So we're going to drag that into our project.
Let's Unity import it, and then we'll attach it to the agent. Let's see how it works.
So here in NN model, neural net model, it's waiting for a model. You can drag this in here, and then that becomes the brain. So instead of there being the brain that's external to Unity while it's training, now it's locked in place, it's learned everything it's going to learn. It maybe would have been better if we gave it a few more steps, but we've trained it really fast, and now...
Crucially, if you're going to deploy this Unity project outside of Unity, it no longer uses PyTorch. It's using something called Unity Inference internally to Unity, which will ship with your Unity binary to do the inference.
So you don't need to package up PyTorch with whatever.
There is no Python dependency from this point on.
All right, so now we're going to press play, see if our little guy has learned how to do it. Yay! Look at him go! Spearbot. Even recovers. Awesome. Good on him. All right, so...
That's a really quick demo of building your own agent using the Unity ML Agents framework. Okay, so tying this back to our 5 points we were looking at earlier, the agent was a little sphere, the environment was a plane with a randomly positioned cube, the actions were change roll force in either of the directions it can roll in, its observations were where it is, how fast it's moving in the directions it can move in, and where the cube is. And it gets a reward when it touches the cube. Very simple. Very, very easy, and it worked with some minimal training. The training in real time maybe took about, what, 10 minutes or less, give or take?
Less.
Yeah, 5-6 minutes. Pretty quick. We already had something with pretty sophisticated behavior for effectively no programming of those rules.
All right, but you probably want to know, how can I extend this to something that's real world or more powerful if I want something that's more complicated than a ball that seeks a cube?
So this is a real-world robot arm. It's called Universal Robots UR3E. It's very expensive or very cheap, depending on where you look at it. So from my perspective, it's very expensive at about $35,000 a unit. From industrial perspective, it's very cheap at $35,000 a unit. This thing is used all around the world in factories. It's an incredibly popular off-the-shelf industrial robot. It's real. It's a physical thing. It sits in robots with other robots assembling cars. Here's a simulation of it. It is a simulation within Unity. In this simulation, the agent that controls the robot at the level of each joint. So it has a discrete control of each joint. It uses a joint index to select the joint it wants, and an action index to move the joint clockwise or counterclockwise or not at all. It has a bunch of observations. It has the current observation. It has the current rotation of every single one of its 6 joints, and it has the position of the cube. The reward at each step is the negative distance between the end effector, so the tip of the thing, and the cube. This basically means the reward is continuous, and it does incentivize the agent to touch the cube.
Or prism.
Or, yeah, well. The episode ends, the step ends when the robot touches the cube, basically. So this is an example of a very sophisticated real-world robot existing in Unity and running using Unity ML agents.
In realistic conditions.
And you could offload this brain into the real robot because the real robot has exactly the same set of features as the virtual robot. Coincidentally, the virtual robot was created using something called the Unified Robotic Description Framework, which allows you to specify exactly how a real robot is put together, joint by joint, length by length, piece by piece. Define that in an XML file, because if anyone loves something more than YAML, it's XML. And then import that into Unity, which Unity has a full pipeline for importing, and it just assembles the model for you. You do not need to model these, they just come into the thing. This just magically happens. And then once you've got this robot in Unity using the URDF importer, you can use it for however you like, for ML, other or nefarious purposes. These robots run on something called Robot Operating System, ROS, which Unity has a full framework to talk to, which means if you were building ML models in Unity that work with these robots, you can control robots using the Robot Operating System over a similar sort of bridge as we're using to train the robots.
So here is an example of where a similar thing was used to train a self-driving car, because you can have a car and it can be in a realistic environment, and we can give it sensors like raycasts that will simulate LiDAR. We can give it a camera on the front that will simulate the camera input that it will get. And we can see that it gets these different layers of input where it can recognize where other cars are, because we know that as it's driving through the world, it can look at its LiDAR raycast and say, what game object type has it touched? It will go another car, and it will learn, okay, when we see this looking thing in our camera, that is another car. It's also learning because it can raycast and ask everything what layer or object type it is. That upper right-hand corner input, that gives it some training data of how it can learn how to infer depth from its 2D cameras. So this is a fully complex simulation where a car has learned to navigate a realistic looking neighborhood in day and night conditions, all different lighting conditions, all different traffic conditions that are all done inside Unity, and this would work if you put it inside that actual car because it has the same information. Here it is again in the night scene where we can see visualizations of its light out the whole way around, and we can see that that doesn't go through any solid objects like it wouldn't in the real world.
Here's a really fun simulation that Unity made early on in the pandemic to show what would happen if infected people were shopping in a typical shopping environment, like a grocery store, depending on certain parameters around the store, like how long they had to stand in line, how long it took to be infected when you were near somebody who was infected, range of infection, whether aisles were one way or not, things like that. So it's parameters that could be used, in theory, to test parameters of a real-world store to minimize people's ability to be infected while you're in it. And this was built using Unity ML agents and allows you to simulate all sorts of crazy stuff about how and why the COVID-19 virus might spread in a store environment. Just kind of shows you the flexibility. I'll tweet a link out to this simulation because there's a WebGL player you can play with. It's kind of fun in a really morbid way.
So that's just two examples of how, well, three examples of how you could extend what we've just shown you about Unity ML agents. But there's also all these different axes. Because it's so modular, it means that right now when we trained a model, it defaulted to an algorithm called proximal policy optimization. But you can replace that if your model that you're wanting to train has some other technical constraints or would better fit a different type of structure. You can use anything from PyTorch, from TensorFlow, or just because it talks to Python, you can actually replace that whole backend with anything that runs Python code. Instead of having a local backend, like I'm just running this on my MacBook Pro, you could hook it up to the cloud. Unity has their own cloud thing where you can say, I want to train this ML agent, go build in the cloud. But you could also hook it up to Docker, hook it up to anything. Instead of using that primitive agent model, like we said, I used a sphere. Paris introduced how you could use the UR3D files, but there's also other sources of standardized formats for input, which means you can represent those real world objects accurately in Unity without you having to do that yourself.
Anything you can get into Unity, basically,
yes.
is fair game.
And you can also have simulations that incorporate some real world data, like photos, like more realistic LiDAR, like sensors, things like that. And when you're done, again, like the robot arm, you take that neural net file, that .onx, or if it's something, if you use TensorFlow instead, it's going to be something else. Depending on what output you use, some representation of that graph, and you can go put that in a real-world robot, a real-world car, whatever you like.
So here's a great example that I love that sort of ties a lot of these things together. This is some pictures of some shopping that somebody might buy at a grocery store. And you might want to make a robot that allows people to see how much the cost of their shopping cart is, or self-checkout just by leaving, like those fancy Amazon stores in the US, things like that. Manually labeling this data, i.e. drawing boxes around it and identifying what it is, in the mishmash of other things it's in, so piled up all on top of each other. Complicated, time-consuming, potentially expensive to make. This is a photo that's been labeled by a human to indicate what each product is. You can actually use something called Unity Perception to generate thousands of randomly positioned, rotated, occluded images and products and spit them out so you can do your machine learning training on that. Unity, because it knows the exact position of all the objects in the virtual scene, even though they're replicas of real-world things, it can give you the tagged information, which you can then use to train in a completely separate non-Unity machine learning environment to build that shopping trolley scanning robot. Really easy to do stuff like this, and you can generate millions and millions of pieces of labeled data using Unity in the time it would take a human to label maybe 1,000. Okay, so that's the end of our talk really. Here's a little summary. Unity ML Agents is a fabulous bridge between all the cool Python machine learning stuff and Unity that lets you build really featureful simulations in Unity. As we all know, game developers, we can do that. And then hooked up to machine learning, so we can have all sorts of interesting behaviors going on. It's not just useful for building bots and AI for video games, it's useful for making things that have behaviors that could be used in the real world, like self-driving cars, picking robots, packing robots, all sorts of stuff. It works with all sorts of other frameworks. You can just use it as a Python bridge if you want, and it really is limited only by your imagination. And by your imagination, I mean anything you can get happening inside Unity. So thank you for coming. We hope you enjoyed it.
All right, so we're going to say thank you for coming, but I'm also going to plug the fact that Paris is on another talk that's been really expertly crafted by himself and also his colleagues about narrative game development and all the different frameworks you can use. They have done a fantastic amount of interviews with other people that work in that area, and that is coming up in the Sounding Theatre at 2:30 p.m. So thank you for having us, and we hope we see you again. Bye.